Ladies and gentlemen, welcome back to your favorite show, Not So Complicated. The show brought to you by Innovation Consortium, the home of the next generation solutions. Oh yes, indeed. Yes, and today's topic is about 3D printers, CNCs, leather machines, and everything. When I went to school, I did not do anything to do with sciences, so and today my main guest is Gonzaga, the only guy who single-handedly has manufactured a robot that he actually uses to cook food. Ladies and gentlemen, Not So Complicated is the name of the show. Right about now, the machines you see, the 3D printers you see on this table were manufactured single-handedly by this guy, Gonzaga. Let me introduce my panel. How are you, Jukes?
Hi.
Well, in more science, at least you have an idea. Glad to have you on the show. Byron, glad to have you on the show. The way you're enjoying the drink, man.
It's a weekend.
It's a weekend. Yes, Mabuya, the Joker, Spider-Man. How are you, sir?
I'm
Good to have you on the show.
Thank you.
And then my main guest, Gonzaga. How are you?
I'm good.
Now, tell us about what is happening here exactly.
Yes, what you see here are 3D printing machines. The way they work is that you have a plastic spool. This is a spool. It's just a thread of plastic that is pulled into the machine. And then there are motors that are moving the bed. This is the bed. It's moving to place plastic on different points to form what you are seeing. So what happens is that it lays down one layer. Then there's a cooling fan here which cools that layer, and then it solidifies and lays down another layer and another layer and another layer. It goes laying down layers in maybe a layer is about 0.2 millimeters thick, which is like a quarter of a millimeter roundabout, or a fifth of a millimeter. So it goes on laying that layer until it forms a full object. And the interesting thing about these machines is that they print their own parts. So if you look at this screen holder, it's 3D printed. If you look at this casing for the electronics, it's 3D printed. This element and this element and this element are also 3D printed. As you can have a look at the casing is an example of what low volume manufacturing is about. To produce that casing for the electronics, you would have to have a mold. And then a mold is like a katiba. Those people who have ever made bricks before, I'm sure Mwami Juko, you know. You have a katiba and then you push in the plastic that is molten and then it takes the shape of the mold. But here, that casing was built layer by layer by layer by layer. So that means that I don't have to have a big injection molding machine, which is maybe about $30,000 and more. I don't have to have a 3-phase transformer. I don't have to have a mold, which is about $6,000, just to produce that one piece. You see, and anyway, I don't need 100,000 pieces
And also
at the beginning, yes, to make those pieces. And also, I don't need sophisticated stuff. So what happens is that using these kind of things, you can basically make parts like this. So you can actually, this 3D printer, its main use now is to print itself.
For a layman to understand, I myself, I need to know what is 3D printing. Samples of, say, probably things we come across.
Can I explain that?
Maybe you can explain.
Yeah, okay. Today I'm not the joker. Today I'm the engineer. Right, maybe to explain to you 3D printing and maybe our listeners and viewers. Everything in life lives in 3 planes. The X, Y, and Z. Those are where the 3D comes from. Yes, exactly. So, for those who did mathematics at O level, there was the X axis, then the Y axis. Exactly. But now, there's a third axis, the Z axis, which I would say caters for elevation. If you go in this direction, actually this is X, this is Y, but now up is Z. hence this. And everything in life is actually in 3D. Like this bottle, it is probably 2 centimeters in the X direction, 2 in the Y direction, and probably 10 in the, so this is 3D. Everything you see is in 3D. So 3D printing is actually printing in all the 3 dimensions. So basically what you see, everything you see is 3D. So 3D printing is creating reality. Like you see a bottle of beer, you want to print a bottle of beer, this machine will print it. The only thing that will change is the material, because it can't print glass, but rather it can print this exact bottle. So whatever you put in there, it can be printed. Probably, as long as you want it in a certain material, probably he will.
So actually, what he's saying is that it will. That's why when we have the 3D model, you'll take it to, you'll export it as what we call a .stl file. Yeah, like when you have an Excel file, you have a .xl. Now for us, the file model we use is .stl. We will take it to a certain software, which will slice it. The process is called slicing. It slices it into layers, and these are X, Y direction. It's like how you get a piece of paper, you add another piece of paper, add another piece of paper, add another piece of paper, until you get a block, a book. You understand? So, but the problem is that every layer takes on a different shape, slightly varying. Now those layers are what is the Z-axis. So it will lay down the first layer in different shape, slightly change the shape on the second layer, and keep adding those layers to come up with a particular object.
Let me uncomplicate it. Okay. The show is good, not so complicated. If I'm to print this bottle, if this machine is to print this bottle, it won't print it as one like this. What it will do, it will print this circle, then print this part, then this part on top of it, until you get to the bottle top. So that's basically
following the mold.
Following the mold.
Thank you.
Maybe to intervene a bit, since we said the show is not so complicated. Then we start putting X, Y, Z, and things like that. We said, now this is kind of complicated. Let us, can you go like please explain how each of those components moves so that we separate what they are talking about.
Okay. Now this particular component moves in this direction, yeah, which is probably the Y direction. This particular bed moves in this direction.
So they are doing
yeah.
this.
So they are constantly moving like this, yeah, yeah, and then this whole element is moving up like this and down, which is which is the Z direction. So this is the Z direction, this is the X direction, this is the Y direction. You understand? So basically what it's doing is that the software interprets the model that you have given it, the slices, and it pulls in this material, melts it, and places it on, you remember those XY coordinates. If you used graph paper and you drew a certain graph using X and Y coordinates, you have those coordinates. So it will drop material here, drop material there, drop material there continuously until it's done with that first layer. Then after that, as this fan here is cooling, it cools that layer such that it solidifies enough to be able to to hold another layer on top. So it's an intelligent sort of like system inside there that works together to come up with that object.
So
yes.
Yeah, I'm sorry to make it simple. So what we are really here is to tell us that you're making these things on your own.
Yes, sort of.
So I would like to know basically what you make.
Yes.
And how do you make it?
What is the inspiration behind this?
The important thing is that we do assembly of most of the things here. Yeah. Now the motors are picked from the scrapyard in Katwe. We pick them from old photocopiers. They use this technology. The rods are also picked from old photocopiers. These lead screws here, what they call the lead screws, are imported. The anti-backlash nut is imported. This part that moves on this lead screw. And then there is what they call the electronics. Most of the electronics, actually all the electronics are imported. but the most important thing is that it's open source. So we put the electronics together, we import what they call this board here, but different version of it, which is called a maker. It's what is the brains of the machine. Then we have the drivers that drive these motors. The circuits that control these motors are also sitting on top of that board. So all those we assemble here, then we program this board to sort of like be able to interpret the functions that come from the SD card.
In terms of percentages, how much is imported and how much is locally made?
Okay, you could say maybe 60 is made. Yeah, everything is assembled here first of all, but like 40% of the components are imported. Yes, and some of them are salvaged from, and then we print most of the parts that hold it together are printed by the printer itself. So if I want to make another printer, I just buy material and then print other parts, which can.
So
so
the
first printer is the parent of all.
Thank you. Is it in biology? It would be an hermaphrodite arrangement.
Yeah.
But this is itself. Yeah.
Okay.
So it's sort of like you just be able. It prints its parts and prints other
How
parts.
many does that printer have? How many kids?
It can have many children. I mean, one printer can have, as long as it still lives.
As of now, how many has it produced yet? How many has it printed?
24. We have produced parts for 24
Your target
printers.
is
Yes. Our target is to make 100 printers. And so we are slowly putting together resources to buy the necessary circuitry, to buy the necessary, motors for scrap, to buy the LCDs, to sort of like, put together the other 100.
I'd like to simplify one thing. You talked about low-scale manufacturing.
Low volume.
Low-volume manufacturing.
Yes.
The simplest thing everyone can understand what I was trying to say, like, an example, like a cake packaging box. If you go to the factory, they have a number they start from.
Yes.
So you can't make an order of I want 2 boxes,
You can't have a
I want 3 boxes.
100
Yeah.
parts. So by local market it means you at the moment you can come to Gonzaga or to Consortium and they manufacture for you
A certain part.
those small numbers, certain part in those small quantities to your specifications. So
For example, it's a very clear example in this case in here. It's impossible to have this thing produced, to go to a manufacturer and tell him I want 10 pieces. They'll say, are you even kidding me? I mean, can you just go back to your country or where you're coming from? Or because you need a mold to actually produce something like that. You see what I'm saying? So the thing is that if you need to have a few things, a few parts, how do you cater for that? Yeah? Then actually this arrangement has come from a need to address low volume manufacturing, because when I went to China, the guys were like, don't waste your time opening up a mold for a box. Yet I had a product that people already loved and were consuming. They said, no, why don't you pick one of these boxes that are already being made? Why? Because those products have already achieved large volume status and they can be actually manufactured in large numbers. And mine has not achieved maybe 100,000 parts, but it has 10,000 subscribers. You see what I'm saying? So the thing is that for you to do injection molding, which is the process by which plastic cups like these are made. I'll get one for you. This plastic cup is made by injection molding. Yeah. To get into injection molding, you should be at least be able to produce 100,000 parts a year and sell them. You see what I'm saying? Yeah. Now the thing is that if you have, even Coca-Cola didn't make that much sales in its first year. You see what I'm saying? So the question is, every manufacturer has to begin somewhere. So how do you then produce something that is legit, that people want to associate with in the market and can work with, and yet does not necessarily have a large investment cost in the beginning? And this is the idea. This is actually the problem I was trying to solve. Remember in the episode where we talked about the problem with the lock, the Nakaboxy, this is how actually this technology is supposed to solve that problem by being able to manufacture the lock together. You get what I'm saying? So that it's one piece and it's not joint pieces, so it doesn't come apart. So this is what, as to answer your question, is part of the inspiration. But also it's coming from way back, because I remember in my final year project 15 years back, when I did mechanical engineering, I built a CNC machine for my final year project. So I started with this, buying a laser machine, and then after a long time of running it, I realized it doesn't make sense. So we then built the CNC machines, which we'll see maybe in another part. And then we said, okay, how do we build machines that can help us produce a carboxy? I lost a deal because somebody wanted a nice plastic part like that, which I didn't have. They didn't want my wooden box. You see what I'm saying? So so when I went to China to try and make it plastic, then they were like, no, we can't open up a mold for you. Then I'm like, okay, so how do I go around this? Also, all this is an attempt to solve my actual problem and actual need to be able, because, for example, most of the banks, the smaller banks, would want to buy savings boxes, but they don't want to order any more than 3,000 pieces. Plastic is very useless when it comes to logistics, because it consumes a lot of space and it's very light. So you fill one container, yeah, and you pay a lot of money to ship one container, you see, of plastic. So the question is, nobody wants to touch 3,000 pieces of what you get. People want to touch orders of 20,000 pieces. So the question is, how do you come in and be able to produce 3,000 pieces? It's by having 100 printers, because also 3D printing, despite it being a nice technology, it's quite slow. If you have 100 printers, that means you can have 100 of these in those 8 hours. So in one day, you can have 100.
Okay.
Yeah. So the question is,
so basically you can, the order will take you just a day.
thank you. So a 3,000 box order, probably I can execute it in 30 days. I can guarantee you it's very hard for you to execute that order from China, injection molded, in 3 months.
So why would you?
Because of one, they have to gear up for production. 2, then they have to ship. Now, because you're not filling a container, they have to wait for your container to fill. You see what I'm saying? Yeah? So all that doesn't make logistical sense.
Have you patented this?
Yeah?
Have you patented this?
No, there is no patenting. Actually,
Open source.
this is open source. This is what they call a Prusa design. Prusa is in Prague. I forget the country, but it's in Europe, just above here. They have a 9-story building that has 300,000 printers, just like this, producing themselves for the entire world. So even their parts are given open source. So all you have to do is to implement. Yeah. Now the thing is that the software that these guys run on is open source.
Yes. Thank you so much for opening our eyes about such a beautiful technology. I would like to know what plans you have. Which plans do you have for these 3D printers?
The first plan was to have a bunch of 24 that we can pilot and work with. Second, we want to go into schools and introduce the technology to the young ones. It's happening elsewhere. I don't see why it shouldn't happen here. The concept that a child can imagine an object, its dimensions, sketch it out, draw it on the computer, and actually make it is a very powerful concept. And it's a concept that even adult engineers probably will struggle with, those that leave schools. So that journey is what we're trying to connect with children. Yeah? And so this should hopefully help us get some funding in to run the project even bigger and to scale it up. Yeah? So because we also want to have the technology adopted at a young level, so that as they grow up, they are able to consume and use the technology. Yeah. So from there, after we have maybe 100 printers, then we can go into low volume manufacturing and perfecting the technology and making sure we can print parts that we can take to market. And as you know now, we have Congo. We could now 3D print gold, you know. Yes, we are East and West African region conglomerates.
So we have a little China and Chirica.
Yes.
Oh yes, thanks so much, and that is a very wonderful plan that you have over there for the country and the continent at large. Now, In parting short, what would you like the world to know about Gonzaga and Gonzaga the printers? Gonzaga enjoy innovations, you know.
Yes, I think I would like to invite those who want to learn about the technology. Yeah, we'll be offering as Innovation Consortium a course for free where you can come and see. Yeah, how things are run. If other people can take on production of some of these things, it would be nice. So that I can just walk into a shop and say, give me this, that, the other, and then I can also assemble, you know? Yeah, because now everything is sort of like have to know, dip your finger in a lot of pies to be able to come up with something. Yes, so, but I would like to say this is possible. It's possible in Africa. It's not only possible in Africa, but in Chileka. Or so I think distributed manufacturing is the way to go, and producing so many products, cottage industries, the whole economy could just
When I made arrangements for someone to make me the key,
yes.
now I'm the
And
it's the device itself. What is print me a leader? Otherwise, this is good. And it's real. Sichiwani.
Alright, thank you so much, David. Byron.
Maybe one point I have to bring out to realize, free printers cannot only be made in Europe or China, we can make them in Jamaica. But I have one more request. Whether I learned a 3D can print a year plastic, I wish it can print this bottle with a liquid in it. This one is empty.
A beer bottle with a liquid in it
Yeah,
as
beer
well.
bottle
A
with
beer
that.
in it as well.
This bottle with liquid in it. I'll be glad.
I have thirsty guys over here. Thank you so much, Byron. Wagana.
Yeah. I wanted to mention two things. That 3D printing is, the applications are so wide that people are now 3D printing buildings. Yeah, the easiest one is with mud, because you can put it in a small spout and build a wall in layers such that it builds up like this. But then it's been around, I think, for about, 40 years now. The first person did it in Japan, didn't patent, then a trio of French such as didn't do it. So the patent came later, but the technology has been around, and I'm glad that years later, it's being assembled here. I think when we
Manufacture the part of it.
yeah, it's the same thing, because when we talked about 3D printers years ago, there were alien things like, if you don't have $3,000, $3,000, you can't get a 3D printer. And I think Consortium wanted one as well. It's now part of our team that's doing this, and we hope for people to build more and add on this.
Alright, thank you so much. Yeah, and thank you so much, dear viewers and listeners. Like we always tell you, I always insist on telling you that we only bring you a bang. Nothing but the best. Imagine 3D printers made by our very own Gonzaga. Before you know it, he has a robot making him food. And probably we shall have robots serving us beer in our bars. Thank you so much. Reach us out on all our social media handles at Innovation Consortium for such interesting topics, for such interesting big innovations. And ladies and gentlemen, endeavor to bring your kids to come through, get in touch with Innovation Consortium, get to learn such, beautiful inventions, beautiful innovations, open our mindsets, because we are sure we can do it. Oh yes. Thank you, ladies and gentlemen, for sparing your time to be with us. It is not so complicated, and Brian is my name. Thank you so much. Peace out.